So it seems that we got everything working. So hi everybody, I'm Simon Lallemand, and I've been working at BlaBlaCar for a bit more than 2 years as a system engineer. And today I'd like to give you feedback on what we've been doing at BlaBlaCar during the last 1 year and a half. We actually migrated 100% of our production services to containers. So that sounds a bit huge like this, and it wasn't very easy. But I'm here to talk about all the steps that we've taken and the tools that we've built to make this migration possible. Next slide. So here you can see the growth of BlaBlaCar. This is a bit huge, and we had to build the platform so it can follow this growth. And yeah, I will explain later why it was necessary to go on containers. But when you have such a growth, you have to be always ahead of time to build the platform more and more efficient, and so your website's always online. Next slide. And yeah, so BlaBlaCar, I haven't presented the company, but I guess most of you know it. It's a ride-sharing company. So we're a website where people can find a ride or propose a ride to share the cost of a travel to go from some point to another. And we are now present in more than 22 countries. That's the infrastructure that we have. So a few figures. We have more than 150 bare metal servers running more than 200 services, and that represents about 3,000 containers, but I'm not really sure. It's probably more than that. So how did we get there? Well, it all started 10 years ago. Once upon a time, BlaBlaCar was created, and we started very small on a simple web hosting, and then it grew a bit more on a dedicated server. Then we bought 1 rack, then 3 racks, and then 5. So you can see the evolution, always more servers, always more things to deal with. So at some point, we had to switch to the industrialization era. That's when you think that the people that you have can't deal with all the servers that you have to bring new tools to help you with that. So we started to write cookbooks with Chef to manage all the configuration of the servers, and it helped us a lot. Then we dealt with the installation of the server using Foreman. Foreman, for those who don't know, it's a software that deals with all the installation of the server, all the phases of the installation, the templating of the installation process, etc. And always in this step, we chose to add previous slide there, another tool called Collins, and that's our hardware inventory. Because when you have only 1 rack, you can still follow what server you have, and you have all in your head. At 5 racks, it's a bit more difficult, and the wiki page is sometimes not enough. So we industrialized that also with Collins. Next slide. The next step was to uniformize all the hardware that we had. At this step, we had to choose whether to keep our bare metal server or to switch to cloud. And we did the comparison at that time, and we decided to keep our hardware because we had the habit of optimizing from end to end. We do our own network. We do pretty much everything by ourselves. So we didn't want to add an intermediary into that. And well, when you can do all this, it's cheaper to have your own hardware. So, but we needed to do something about all the different kind of server that we had. So we decided to limit the models of server that we bought, and to buy one rack at a time. That allows us to outsource all the tasks that happen in the data center, the installation of the servers, the cabling of the servers to the switches and everything. So now engineers at BlaBlaCar don't need to go in the data center, and that's a huge step because it wasn't very interesting for us to go to change a disk or something like that. The next step was to abstract the hardware, because once you have all the same servers, you might have different workloads that you want to run on those servers. And sometimes very small workloads, sometimes a workload that take the whole server, but that's very rare. So we needed an abstraction above that. So at that time, there was two possibilities, the virtualization and the containers. Virtualization was, well, efficient. It was proved to be, there was lots of tools around that. And containers, well, it was very new and not many people used it in production. So we chose containers. No. Actually, the answer is more like, well, we think that containers is more the future. It's more the way to manage services. So it's a better way to manage services, and there is a less overhead than with the virtualization. So that's why we chose containers. And I might admit that the challenge was also interesting. So now from the choice to the production, how did, once we did that choice, did we go to the production phase? Well, first, we started experimenting with the runtime that existed at that time. So first it was with Docker. And pretty quickly we realized that there were some missing things in Docker and some other things weren't very stable. So we started also experimenting with Rocket. And lots of things were better in the system point of view in Rocket. For instance, the networking part, or the fact that there was no daemon. So other things made us choose Rocket over Docker for the runtime. Then we assembled among the people of the team a task force to create the workflow that would allow us to create the container images and to run them. So we had to have a workflow that worked better than the previous one. Otherwise, the migration would have been a failure. So what we did was, we had this task force that would iterate lots of time, and from time to time we did some workshops with all of the team to validate if the workflow was working or not. For instance, in the first iteration, we decided to build the container images with Packer and Chef, because we knew Chef and thought it would be a good idea. But actually, we realized that it was very slow to proceed with so many tools and so many layers, and it wasn't very efficient to build container images. So at some point, we decided to create our own tools. We started with some bash scripts, and as the complexity grew, we built our own tool. Well, our own tools, because we made several. The main one is called Digger, and I will talk about it later. In the end, we reached the target, which was to migrate to the majority of the production by the end of 2015. So the new infrastructure, what we have now at BlaBlaCar, first, all our servers, the new servers that we buy, they all run CoreOS. Why? Because, well, it's pretty simple to install. It has the latest version of the kernel of lots of tools. And also perfect to run containers. It was made for that. So we decided to install all the servers. And it had a pretty good impact on the migration, because since all the new servers were on CoreOS, it meant that if we wanted to have more capacity or more services, it had to be on container, because we didn't have a choice. There was no place left on the old servers. Then, as I said, we run Rocket for all the containers. Everything must run in container. Everything is a Rocket container. We heard that we were one of the biggest Rocket deployment in production. That's always good to hear. And we're pretty satisfied with the choice of Rocket because, well, it's very stable and it's rather simple. And modular. So we have the team of Rocket is also listening to the suggestions we made, and well, it's a good relationship. Now I'd like to talk about the way we build the container images, because that's the hard part, right? Well, maybe there are also other hard parts, but this is the first one that you think of. So as you might know, Rocket is based on the app container specification. The app container specification defines the way an image is built, the way, well, how an image is composed, and how it is run, and everything. So there can be several implementations of this specification. The main one is Rocket, of course, but however, there are other ones. Well, this is important that we have this specification, because when you're creating your own tools, you have something to rely on. And that's what we did when building, when creating Digger. So with the workshop that we made with all the team, we found out some very important things for us. First of all, it had to work for everybody in the team. We wanted everybody to be able to build container images, and not only a small group of people. So we had to do something simple enough for everybody to understand, for the newcomers also, because we are hiring a lot of people. Something that will make quick builds, and something that if someone is looking at the code that you made, would understand what you wanted to do. Another important thing is the templating at container start. What we mean by that is that we want to be able to change the configuration of the software we're running in the container without rebuilding the whole image. So that's something that we implemented in Digger, and I will explain it how it works just in a few slides. And of course, wanted a good integration with Rocket. We decided to go directly open source for this project because, well, we think that it can be useful for other people. So it's on GitHub. Here is what a container looks like from Digger point of view. So it contains all the instruction about the way the scripts to build the container image and the configuration of the application. So that's a standardized structure, and you might think, well, there are some concepts I know. Yeah, because it was inspired by the configuration management tools, Chef, and etc. You can see there are attributes, there are templates, and the build contains a script to install the software. So first, the SCI manifest. The SCI manifest is actually, it contains all the metadata and the name of the image, what you want to run, what is the first process to run, etc. So we made an abstraction over the SCI manifest defined by the AppC specification, because we wanted something very simple, remember, and the AppC defines a very big JSON that's difficult to write for people, and contains a lot of things that you can easily put defaults on. So here we put only the relevant information in the SCI manifest, and everything else is completed by Digger. So that's all you need for Redis image, for instance. You just define the name of the image and what process it will run when we start it. A very important thing that we run only one process per SCI. And when we need several processes to talk to each other, etc., we're using the pods that are already present in the specification in the FC specification are supported by Rocket, and we'll explain later what are the pods. So here, you can see also that we're using the dependencies. That means that we can compose our image from other images. For instance, here we have the Elasticsearch image, which has for dependency Java and Debian. So each image contains only the minimal files that are needed for this application. For instance, in Elasticsearch, we have only the files for Elasticsearch, but not Java and not all the libraries from Debian. So we have lighter images, and we can make evolve the dependency without touching to the upper image. What happens with Rocket when you have dependency, it actually extracts all the dependencies before extracting the image that you want to run. There's no overlay or something like that. If we go back to the tree directory of an SCI in Digger, let's take a look at run levels. So we have several run levels defined. The first one is the build run level. It actually contains all the scripts that are needed to build the image from the inside of the container with all the dependencies loaded. So if we take a look for the Redis example, next slide, please. That's all we need for Redis image. We just installed the Redis server with the apt-get because we have this dependency. We have Debian, so we have already apt-get in the image, and we installed like this. Another thing that we can do is use another run level called builder. Builder is slightly different because you build from the outside of the container. So here you can see that I define dependencies for the builder, such as SCI Go and SCI Git, because I want to build an SCI for our binary Go synapse, and we want to build it at the same time. So I have an SCI manifest just like this, and you can see that in the end I execute the binary I have built. And if we take a look at the script that was used in the builder, we actually have as dependency Git and Go, so we can Git clone our repository, Go build the binary, and copy the binary in the rootfs of the final SCI. That way, in my SCI, I only have the Go binary and nothing else. But we can go further. For instance, if I don't want to use Debian as base, but let's say Gen 2, I could use the Gen 2 stage 4 as a builder and decide to build LHTTPD SCI. The script would look like this. Next slide, please. Next slide. No? Okay. So in the script, imagine that you have just emerged LHTTPD, and yes, like this. And it will install in the rootfs of the final SCI only LHTTPD and its dependency, but nothing else. There will be no package manager, no other libraries that are not needed by LHTTPD. So you can have very light images, and you can think about Digger as a way to build packages, where the packages would be container images. So that's not something where we are now at Baraka, but that's something we're thinking of, because, well, it can bring a lot of stuff. So right now we're only based on Debian. We'll see later. So next thing, I said that templates were very important to Digger. That's because when we define templates and attributes, they are all stored in the SCI, and they are not resolved during the build. They are only resolved when we run the actual image. So in the SCI, we store default templates, default attributes, and we can override those attributes either if this SCI is a dependency of another one. So we can override like this. We can override with the pod mechanism, so we can put attributes at the pod level, and we can override it with an environment variable when we run the container. So it looks just like this. It's Gotime Rating. So for Redis, for instance, I can customize the Redis port and have a default attribute just like this, defining the Redis port on 6379. We have then another run level. It's called pre-start early and pre-start late. Those run levels allow us to define scripts that you want to execute before the templating is resolved or after the templating is resolved when you run the SCI. So, for instance, if we are running a container for a database, you might want to initialize the database, or you might want to sync with something. I don't know. You want to execute a script before executing the script, before executing the main application. So that's where you would do it. And you can also do testing. Because, well, you have your container, but then you want to test if it's really working, right? So all we've implemented right now are batch scripts. So we have a first file that's called wait.sh that's just here to wait for the container to be ready to be tested. And then we have all the batch scripts. For instance, for a container, for an Nginx container, we might want to test if Nginx is running and if it's listening on the port 80. So just to show you a few commands that Digger can do, we can use Digger init that would create the directory tree that we've just seen with just the dummy information. You can use Digger try that would resolve the template and just check if you've done your templates right before building the container, because when you build the container, run it and realize that you forgot an attribute, well, that's too bad, you have to go all over again. You have Digger build, just used to build the container, Digger test to execute the test that you've written. Digger install would put the image that you build into the local store of Rocket, and Digger push would upload it to a remote repository. I talked a lot about pods. What about pods? Well, pods are a grouping of SCI. An SCI is a single container. When you're creating a pod, all your containers will share the same context of execution. You might have heard about it in Kubernetes. They're using the same concept. So they're sharing the network, they're sharing the PID space and everything. So that's useful, for instance, if you want to create an application in PHP and you will have the web server, let's say Nginx, and the PHP. But you want this to be grouped in the same context. So here you have a definition of a pod. That's a pod manifest. It looks like an SCI manifest. And again, we made an abstraction over the pod manifest that's defined by the AppC specification to make it simpler. So we can pin the versions of the SCI we're using, and we can override also, like I said, the attributes defined in the other SCI. For instance, if I have the Nginx image that has a generic configuration, let's say it can do a reverse proxy, but it can also serve a PHP application. Well, here I would configure it to be in the mode where it serves a PHP application. And then you just have to run the pod, because Digger would have created all the images you need, and you just rocket run, and that's it. But, well, you don't want to run it by hand. So, well, I explain later how you're doing that. But first, you want to contextualize the pod. Let's say you want to use the same image on your development VM and on the production, because that's easier, right? So you could override the max memory used by Redis, for instance. And as I said, you can do that in the pod, but that's not the right place because you want to test the same pod on your development VM and on the production. So we're doing it in an environment variable. And template override is a special environment variable that's recognized by Digger as containing all the context that you want to pass to the pod that you're running. And then, well, you just use systemd because it's easier to watch if your pod is running or not. So all you have to do is rocket run the SCI of your pod and pass all this context. And as you can see here, we have some kind of Go templating. That's because you don't want to manage all this file by hand. So we created another tool, and it's called GGN. So as you can see, there's no logo for this project. It's on GitHub, but it's very specific at BlaBlaCar, and you might want to look at it to just get some inspiration, but you can't use it like this in your company. And at Baraka, we use GGN to manage all our services and in all our environments in our data centers. So what it does actually is providing an abstraction over Fleet. Because well, we wanted to go simple at the beginning. We didn't want a very complex orchestration. And Fleet was perfect for the start. So we have a single tree directory defining all the environment and the services. And everything is in Git, like this. And so everyone in the team can commit in this tree directory and use GGN commands to update the services that are running in production. All right. So here is an example of a service manifest in GGN. So it would run a pod Redis on 3 nodes. And all you have to run just after that is GGN, the data center here is representing the environment, prod data center 1. Redis quota is representing the service that you want to run, and update. And with that, GGN will create all the units, the systemd units, and launch them with Fleet. And since it's using Fleet, we can also use other commands from Fleet, such as journal. Now, when you have done that, maybe you have you're managing your services in a very static way, and you're using DNS for each other so they can talk from one to another. Well, when you're starting using containers, you might want to start lots of containers for lots of different services, and DNS, well, it's there are TTLs and everything, and it's not very reliable way to talk to your services. So we decided to put in place some kind of service discovery, and we didn't want to go from scratch this time. So we used Nerve and Synapse from Airbnb. So in Nerve and Synapse, I will explain in a slide just after. And this project was working pretty well, but after a few months, we decided to rewrite it with more features and to rewrite it in Go. So we put also that on our GitHub. So what is exactly Nerve and Synapse? Well, let's say you have your front server and you have a database. So your front server needs to talk to the database. So next slide, please. Yeah. So here you would have a program called Nerve that will monitor the database and check if the database is OK or not. Next slide. Like this. Next slide. And then it will report on a key value storage. Here we use Zookeeper, that the service is OK. So it will write in the database that the database node 1 is OK. And then on the other side, we have another program called Synapse that's watching the node database and checking if there are other new nodes or if the nodes are changing. And we have also on the same side an HA proxy that is reconfigured by Synapse. So that way, the front server talked locally to an HA proxy. They are all in the same pod. And this HA proxy redirects the request to the database. So here, that's where we are. We have 100% of our production running with this setup on containers. And everybody in the team is doing containers, so I can guess that we can call it a success. But there are many steps that we want to achieve now, because some of the steps are not automated. There are still too much human work. So the next thing we're working on right now is Rocket Netis. You might have heard of it. It's the combination of Kubernetes with Rocket as a runtime, and we hope that it will eliminate some work that's not very funny to do. So thank you, everyone. Do you have questions?
Hello, thank you for the talk. I appreciate your way to use containers rather than going to Docker. Though nowadays, would you reconsider if you were starting your project to use Docker, or would you stick to an approach more open?
To an approach more open?
Yeah, like based on specifications and following the specifications like you did.
Well, I think that it was, we knew we were taking a risk when we did that, but it was feeling more right to go that direction. So, and now seeing the things, how the things have evolved, I think that, well, you can see that now Rocket has reached a stable level, because when we started it was only in version 0.2. There was a risk. Now we're very confident that it's a serious alternative. You might have heard that there's also DOCI that's coming out, and we're watching this very closely, because it would reunite the way of building container images from Docker and from Rocket. So that would be a very good thing. People could choose after what they want to use. But well, I don't know what I would do now, but I certainly don't regret what we've done. You can also ask, vous pouvez aussi poser des questions en français si vous voulez.
Hello. So I was wondering if you will change your service discovery application with Kubernetes, or would you stick to your Go Synapse and Go Dev tools?
Right now, this is not the priority. The main thing that we want with Kubernetes is the automatic placement of the containers, because that's something that we don't have with Fleet. Right now, we're pinning the containers to some machines. So you might think that it's not very easy way to do it, but it's very rare that we lose a machine or that we have to move a service to another one. And even when we have to do this, it's only a line to change in the configuration of GGN, and then a command to type. So it's pretty easy. But we want to eliminate this step. So that's what we want to do with Kubernetes. And for the service discovery, we'll see. For now, we have something that's working, so we're not changing it.
Now you're working with Kubernetes and your service discovery for your tests? Maybe?
Yeah, that's not a problem, because okay. you're not obliged to use the service discovery in Kubernetes. You can, it's called services in Kubernetes, but you can just ignore that part of the project.
Thank you. What about persistent data? database?
Good question. Well, as I said, containers, especially database containers, are pinned to a specific server, and we have storage on all our servers. We don't use shared storage because there would be performance issues, I think, with that. So we're using replication at the application level. So, for instance, for MySQL, we're using Galera. So we have a cluster replication with Galera, and the data is stored locally.
Okay, I think between the fronts and the base it looks pretty clear. But what about, for example, load balancers? Is there also in containers or in bare metal? Thank you.
Yeah, we also have our load balancer in containers. And what we're doing actually is, since we're controlling our network, we're using ExaBGP, which is an open source project, to announce the public IP on a specific container, and then the traffic goes to the load balancer. So that's what we do with all the containers that need public traffic.
Another question: how do you handle patch management? Did you build specific tooling? I think of transitive dependencies between images that you have to rebuild and redeploy a lot of containers that were based on the same root image. How do you do that?
Well, we have a tool that can calculate the dependency between our images. But right now, we're in the process of automating all the automatic rebuild of everything. It's not completely, it's not done yet. It's not in production, but that's something that we want to do definitely. Especially since
that's really a subject you have to cover. I mean, if you do migration to containers,
yeah, of course.
It's not that easy.
Well, we know when we did this migration, we did in a bit less than a year. For 80% of it, and we had to take some shortcuts, and the orchestration one was one of them. The rebuilding automatically all the containers when we change one was also one of them. But now we're fixing this, and we're creating all the bricks that we miss.
Okay, thank you.
Can you repeat the question so everyone can?
As this is production servers, how do you manage monitoring?
So monitoring, first we decided not to change the monitoring. We were changing a lot of things in our systems with the containers and this migration. So we're monitoring things with Zabbix. And the first thing that we did was to have a Zabbix ACI in each pod that we wanted to monitor. And each pod would be seen by the Zabbix server as a different host. And since a few months, we're also working with Prometheus to have a more service-oriented monitoring. So we plan on keeping Zabbix for all the host-based monitoring and monitoring the bare metal. But for all the service, aggregating the different services, the different containers that run the same service, we're now using Prometheus. No more questions? Thank you.